All right, welcome everybody. Today we're going to be looking at this topic here, which is going to be vector fields. And on screen here, you're going to see this definition that I have for these vector fields. And the definition basically states that we can define a vector field either in a two-dimensional space or a three-dimensional space just by taking any coordinate and inputting that coordinate in terms of x, y into the actual vector field function. All right, now this can be done for a two or a three-dimensional space. All right, now as we start looking at this, the notation that we're going to be using is going to be capital F with the little vector notation right up top. So it kind of looks like a function. The only thing is that this is going to be a vector function. All right, this is going to define some vector field. So when we start looking at this, we then have to start identifying, well, why is it important to analyze vector fields, right? With the process that we're going to need and that we're going to be going to, they're going to be very, very useful. Now, when we work with vector fields, oftentimes we like to think of vector fields as kind of like fluid flow, airflow, or gravity. Anything that applies some type of force or that moves in a certain direction, we can model with a certain vector field. All right, so I'm going to show you a quick, let's not say sketch, but I'm going to show you a quick rendition of this on GeoGebra. All right, so follow me along. All right, so I'm here on the GeoGebra classroom that I have for us. And if you look down here, I have this vector field example 1, and that's the one that I'm going to click on here. So as I'm looking at this vector field example here, what I did was I actually took the liberty over here to input the vector field that you want. All right, so this current vector field, this function is being denoted here. This is a two-dimensional vector field. So in the x component, here we denote it by the I hat. We have x minus y as our function. And in the y component, we just have x as our function. And notice that this vector field kind of creates almost like a circular flow. All right, it's moving in a circular fashion, but not exactly a whole circle, right? The vectors in quadrant 1 and in quadrant 3 look like they're moving a little bit faster than the vectors in quadrants 2 and 4. The vectors in quadrant 2 and 4 look like they're moving more at a constant or slower rate. All right, so if we go ahead and if we then alter this, let's say we alter it and we have negative y there. There we go. Now my vector field actually changed, and now it gives me more of that circular flow for this particular vector field. All right, and again, you can experiment with this. It's on GeoGebra for you guys to move at your liking. All right, you can play around with this and you can input different functions and see what all those different functions do. All right, now what we're going to be in the process of doing is we're going to be given a vector field, and with this vector field we're going to want to put some sort of curve in this vector field. And then we want to see if we put an object on that curve, how is this vector field affecting that object? All right, in what way does it affect it? And that's what we're going to be looking at. All right, now we can also do this for three-dimensional vector fields, and I have a different example for that on GeoGebra. All right, so let's see if we can go back here. All right, now I don't have it uploaded, but I'll show you off of my personal collection. Let's go back here as well. Let's see, is it going? There we go. All right, so this example I will upload at a later time. And this example is just this example of a three-dimensional vector field. All right, so let me unclick that. Here we go. So if you see this vector field, I scaled all the vectors down to be unit vectors. All right, that way we can see them a little bit more clearly. Typically, if we don't draw them as unit vectors, they get very, very convoluted, and it's really, really hard to see what the vector field is doing in RSpace 3. Alright, so that's what we want to see. Now, don't worry, I'm not going to have you sketch any vector fields in RSpace 3 because, again, they look very, very intimidating to actually get. Alright, so come back to this example, the one that we were just looking at, this vector field example. What I want you to notice here is that I also scaled all the vectors down to unit vectors here. Alright, typically the faster a certain object moves through a certain portion, or the higher the slope of these vectors typically have a longer arrow in that direction. Alright, so just kind of keep that in mind. I scaled all of these down to be unit vectors. Alright, so let's go back into the actual portion of the class. Alright, follow me along. Alright, here we are. So what I want to do really quickly is I want to go ahead and I want to sketch one of the vector fields that we were looking at a little while ago. So let's go ahead and sketch the vector field. So this vector field is going to be a vector field in xy given by negative y in the I component and then given by x in the j component. And again, you already saw the vector field. This was one of the vector fields that I was working with in the examples on GeoGebra. But what I want to do right now is I want to go ahead and I want to be able to sketch this. That way you can see how GeoGebra is interpreting this and how it's beneficial to go ahead and scale all of the vectors down to unit vectors instead of looking at them with their given lengths. Alright, here we go. So I'm going to label this as y. This one's going to be as x. And what I'm going to do really quickly is I want to create some sort of table. That way I can keep this organized. Alright. I'm going to move this. There we are. Alright. Oops. It didn't like it for some reason. It's okay. Nope. Alright, bear with me, guys. Bear with me. No. Okay, it's okay. Alright, so what I'll do is I'll just create a table right over here. So I'm going to start creating some of these points. Oops, excuse me. I'm going to start creating some of these points, call them just x's and y's. Alright, that's going to be one of the first things that I'm going to want. And then after that, I'm going to start creating these vectors that I'm going to be observing. So the next part is that I want to create these vectors off of the points that I initially choose. So what is this going to look like? Well, we're going to go ahead and we're going to get this done right now. Let's build this table. There we are. Perfect. Alright, so let's go with one of the ordered pairs. Alright, and you can pick any ordered pairs that you'd like. Alright, but more specifically, I want to choose some ordered pairs in quadrant 1, in quadrant 2, in quadrant 3, and in quadrant 4. So I'm going to go with some of the easier ones to choose. Let's go ahead and let's choose 1, 1. When I substitute in the x value of 1 and the y value of 1 into my actual vector field, my vector field for this input of 1, 1, well, the y coordinate, this y coordinate now becomes -1, so that's -1, and then my x coordinate is just 1, so that stays as just 1 in the j coordinate. This vector here is given by vector -1, 1. And again, this vector exists at the point 1, 1. So I'm going to go over here and I'm going to give this a scale. Here we are. Alright, that's going to be 2. That's -2. It's -2, and then that's 2. All right, so when I go over to 1, 1, that's where my vector starts. That's this piece right here. And then once I substitute it in, I need this vector, and this vector goes in the x component, -1, so -1 in the x component, and then it goes up 1 to here. So that vector looks like this. There we are. Now I'm going to choose a different vector. All right, and I'm going to do this different colors, that way you guys can see all of the different vectors that are going to go along with this. All right, so let's go ahead and let's choose a vector in quadrant, or a point in quadrant 2. Let's let that point just be -1, 1. If we substitute this into our vector field function, our x component is -1 and the y component was 1 that we chose. And subbing that in here, I get the y value being just -1. That's in the I component, and then the j component, or the x component here, is at -1. So I have -1 in the j component, and that gives me a vector of -1, 1. So when I'm here at -1, 1, my vector here is -1 in the x component and then -1 in the y component, which means this vector looks like this. Let's do a different color. Let's choose a point in quadrant 3. So the next point in quadrant 3, we're going to be looking for -1, -1, making our substitutions into our vector field for this point. The y component was -1, so that's going to be -1, so that's just going to be +1, plus x, so that's going to be -1 in the j direction. And it looks like this. So at -1, 1, here we are. In the x component, I go +1, but in the y component, I go down 1. And it looks like this. And then finally, let's choose a different vector, a different point, and we're going to choose the point 1, -1. There we are. So when we choose this point 1, -1, then again, make all of our substitutions in here. We're going to get -y, so that's just going to be I. And then we're also going to get plus the j component, that's the x component, which is just 1. So that's going to be 1 in the j component. And this vector is just 1, 1. So from here, x component, we go over 1, y component 1. Bam, there we are. So that's what our vector look like. That's what our vector field looks like. And we can choose different vector points in different locations within this quadrant. You can also start choosing points, say, on the x and y axis. So let's say we had chosen 0, 2. All right, so 0, 2, we're right up here. On that point, we're going to go to our vector field, which is 0, 2. And again, the y component, that's -2 in the I, plus 0 in the j component, which means this vector is -2, 0. So at this point, -2, 0, so we're going to go -2 in the x component, 1, 2, here we are, but we don't move anything in the y component, which means this is my actual vector. And if you keep doing this over and over, you're going to start seeing that these vectors kind of move in this direction, where the more outside that you go from the origin, or the more further away you go from the origin, you start moving away faster and faster and faster. Right? So this is kind of that example of the vector field. And notice sketching of the vector fields take a long time, and that's why I like to use more of the GeoGebra process for this. That way we can see the vectors very quickly, and we can then just identify them and work with them. All right. Now, there is one specific topic that I want to hit on. We do have what is known as a gradient vector field. This gradient vector field is built off of gradients for some function of f that we are given. When we look at this vector gradient field, it just is the gradient of the function that we're looking at. And that gradient is what's going to create this vector field. All right, so oftentimes when we look at these vector fields, we want to look at these gradient vector fields because they make really, really good examples. So let's go ahead and find the gradient vector field of the following functions. Alright, part A. We're going to go with f of xy is equal to x squared times sine of 5y. And we're going to see if we can build that gradient vector field. And then we're also going to do part B, which is going to be f of xyz, which is going to be given by z is z times e to the power of negative xy. There we are. So let's look at the first example, part A. We need the gradient vector field, and this gradient vector field is only going to have two different components for that vector because, again, we're only given these two different variables, x and y. So when I look at my gradient vector field, I just need to look at the partial derivatives. What's the partial derivative of this function with respect to x? Well, that's just going to be 2x sine of 5y. What's the derivative of this with respect to y? Alright, so that's just going to be 5x squared. Oops. Cosine of 5y. And that's it. So what we would then have to do is we would then want to sketch this vector field right here. If we can sketch that vector field, then that's awesome, because then that's going to be the function. This original function produced this vector field, or I should say that this function produced this gradient vector field. Alright, let's look at the next one, part B. Gradient of f. This gradient of f, again, because we're given three different variables, it's going to have three different components. So we're going to take the differential here with respect to x first. So taking this with respect to x, we're still going to get e to the negative xy, but then if I took the derivative with respect to x, I should get negative yz to be multiplied. There we go. Perfect. Taking the derivative with respect to y, that should give me negative xz e to the negative xy. And then the last one, taking the derivative with respect to z, just gives me negative e to the xy. And there we are. These are how we obtain these gradient vector fields. Alright? So, we're going to move on from these vector fields in just a minute. Alright, so here's going to be this quick definition. That says that a vector field f is called a conservative vector field if there exists a function f such that the vector field, the function of the vector field, is equal to the gradient field. If f is a conservative vector field, then the function f is called a potential function. And And in our process, in our work, we would like ideally to work with these potential functions. So if we have a vector field that is conservative, then we're able to find this potential function. All right. Now, this is what we want to look at, and this is how we want to observe it. All right. Now, let me give you a quick illustration here, or a quick example. Say that I have a vector field as y in the I component and then x in the j component, and this is a conservative vector field. If it's a conservative vector field, then we should be able to find some potential function. All right. So since we have a conservative vector field, we need to find the potential function f. So the potential function of my vector field is f of xy is equal to x times y. And we can double check this, right? Because if we then go ahead and take the gradient of this function, the gradient of that function, partial with respect to x is just y, partial with respect to y is just x. And this right here is this vector field that we were initially looking at. In other words, this function f is just the potential function for that vector field. All right, so that's going to wrap it up for the topic on vector fields. Now, the next topic that we're going to be looking at is going to be line integrals. All right, so stick with me on that, and we'll be back shortly.